Yes, thank you. And of course, thanks to the organizers for organizing this beautiful event and for inviting me, of course, yes. I'm sorry for the long title, but I didn't know how to formulate it otherwise without giving the impression that I did something that I hadn't done. So I will say a few words about why this title is so long a bit later. But before I forget, I should say this is joint work with a few people. The first is Alessio Marrani and Heiko Dietrich. Oh. And Paolo. Faccin. And well, they're sort of different, all very different contributions. So Alessio is actually a physicist, and he works in theoretical physics, things like high energy physics and black holes and that sort of thing. And in his work, he needs embeddings of real semisimple Lie algebras or real reductive Lie algebras in semisimple Lie algebras. And he sort of suggested to me to compute lots and lots of tables of all real forms of ranks up to 8. And so that's what we did. And the algorithms that were used for that were developed together with Heiko and Paolo. Okay, so that's more or less the thing. Okay. So what's the problem? Well, maybe an easy version of the problem. So let maybe G be a maybe simple Lie algebra, and the problem is to find all, let's say maximal, or well, let's say all, well, maybe maximal. Put it in brackets, maybe semi-simple subalgebras of G up to some equivalence. Usually the number of semi-simple subalgebras will be infinite, so there's no hope you can do all, but you have to have some equivalence. And possible equivalences that have been considered here are first of all conjugacy by some group, let's say by the adjoint group or something, or by the automorphism group if you like. Well, you can take several groups for that. Or a thing which is called linear equivalence, or just isomorphism. Sort of isomorphism is sort of the weakest one, where you just say, well, I want to know if A2 embeds in A3 or something, which of course up to isomorphism obviously does, but anyway. Linear equivalence is a bit complicated concept. So two subalgebras are linearly equivalent, just to say it very quickly. In a big algebra, if you take any representation of the big algebra, the induced representations of the subalgebras will be equivalent representations. And that's a bit of it seems maybe a bit of a difficult concept to deal with, because you have an infinite number of representations. But actually linear equivalence is easier than conjugacy by the adjoint group. And as equivalence goes, it's very close to conjugacy. So in type A, it's equivalent. In type ABC, it's equivalent. For example, these two equivalences are equivalent. Yes. So it's the same relation, so to speak. And in other types, you get very few examples. So you get examples where you have non-conjugate subalgebras that are actually linearly equivalent, but not many examples. Okay, so this is a good substitute, and it's actually easier to deal with because of some reason that I'm not going to go into. Okay, so what has been done about this? Well, at least some previous work. So I'm interested, as in the title, in the real case. So I'm interested basically in C and R now. So if you do it over C, the big sort of first step in this was done by Dynkin in 1950. Well, maybe plus or minus. I don't know exactly when, but it's around 1950. And he has two big papers. Yeah, one for classical types and one for the exceptional types. And well, many, especially in the second paper, there are many ideas and theorems and theory, and it's a long paper. Okay, so what and a lot of results. Yeah, so he has maximal subalgebras, and well, I cannot really say all that he did. And then we have a paper by Lorentz and Gruber from 1972, and they do actually what they do is they apply Dynkin's method for the exceptional types to the classical types up till rank 6. Yeah, so classical until rank 6, and again they have lots of tables and things. And okay, and then we had a paper by Minchenko. I think this is 2006, where he finds in the exceptional types he finds the simple subalgebras, so not only the maximal ones but all simple subalgebras up to equivalence. Yeah, up to conjugacy. Okay, and actually also corrected some errors in some lists of Dynkin. No. And actually, I did some work on this as well, something like that. And I just used computers to get lists of all semi-simple subalgebras of the Lie algebras until rank 8, up to equivalence. Up to linear equivalence, sorry, up to linear equivalence. Okay, so that was over C. Now what is there over R? There's much less. So R over R, the problem is much more difficult. But there's a series of papers by Cornwell and also Ekins, say 1971, 1972. So I think the first three were just by John Cornwell alone, and the last two in collaboration with Ekins. And they develop methods to do it over R, and they find lots of embeddings, but they don't do it systematically. So they have well, let's try this embedding, then we try that, and then the third and the fifth and the sixth and so on. So there's no table that says, oh, well, here if you have your real form and you get all maximal subalgebras or something like that. Okay, so that's one. And then there is the other one is Komrakov. I think that's 1990. Who produces lots of tables and actually claims to completely solve the problem over R. But he doesn't say a word on the methods he used. They are just tables, and actually they're not entirely free of error or of omissions. Yeah? So you actually some things are remarkably correct, and you wonder how the hell did they do that? But there's no word about it. Yeah. So yeah. So okay. So that's more or less what's there over R. Okay. Yes, so what was our contribution in the work with Marrani? So what did we do? Well, we have algorithms to construct embeddings. On which I will say some words later, and which are implemented in GAP4. And we have a package, so it's which is called co-real, something like that. So it's a get package. This is a get package that we wrote together with Heiko and Paolo for dealing with real forms of semi-simple algebras, right? And this is heavily being used in order to implement these algorithms. And the acronym actually means computation with real groups. That was actually the acronym of a project proposal. A project that we had, I don't know, when is it? In 2012 or something like that, I think it was, wasn't it? So and that's the reason why the package is also called that way. Okay. And what we produce is tables with maximal, reductive subalgebras of simple real Lie algebras of rank until 8. Okay, so rank 8 is a canonical choice to stop, because then you've done E8 as well. Okay, so okay, and in the paper there's about, I don't know, 50 or 60 pages of tables. So also going on would make it sort of very, very uncivilized in length. No? Okay, so that's what we did. Yes, and maybe I should say something about the maximal. So there's real forms of embeddings of maximal. So what we do is actually study the following problem, which is given. So let now GC. So I always use the superscript C if it means complex. Okay, if there is a C, it means complex. If there's no C, it doesn't really necessarily mean it's not complex, right? But if there is a C, it means complex. Okay, so let GC be a simple Lie algebra over C, and let maybe G be a real form of GC. Let maybe AC in GC be a maximal semi-simple or reductive, but I will just stick to semi-simple for the talk, because it's a bit easier and I don't have to introduce other notation. So we take a maximal semi-simple subalgebra of GC. Okay, and what we want to do is find all, let's say, subalgebras of A, let's call them A, or A hat of G, such that A hat C, right, is equivalent. So A hat C in GC is equivalent, whatever equivalence you're using is equivalent to the one you started with, AC. So A hat C is just the complex span of the real subalgebra. Okay. So what you want is real forms, so real subalgebras that are equivalent to the maximal complex subalgebras. Of course, it can happen that you have in the real world you have a maximal subalgebra whose complexification in the complex thing is not maximal, because all of a sudden over C there appears a subalgebra in between that doesn't have real forms in the real world. You see, and actually Komrakov has this case, and he has some list, but that list is very difficult to understand, and we can don't have no way to verify anything about it. So so we don't do that. No? So there's no. We just do real forms of the maximal complex Lie algebras. Okay. Okay, good. So maybe I will erase this. Now, subalgebras, they come in two flavors. regular and S. Okay, so we have two types of subalgebras, regular and S, where S is just a letter. Okay, I don't know. I think it was introduced by Dynkin. At least that's the earliest reference I know to S subalgebras. And S just means not contained in a regular subalgebra. Okay, I will come back to that later. Anyway, so we first look at the regular subalgebras. To say what it is, a subalgebra is regular if it is normalized by a Cartan subalgebra. Okay, that's the definition. Actually, this morning Adam has been talking about this, because in this picture he was classifying the regular subalgebras. So I don't have to explain that anymore. Okay, so we want the maximal regular subalgebras. Okay, and again, let me say a few words over C. And this is done an algorithm. There is an algorithm by Dynkin, which basically consists on drawing a picture like this and then adding a node and then erasing some other nodes. Okay, and it's based on some facts. So based on some facts, well, first of all, there is a unique Cartan subalgebra, let's say HC of GC up to conjugacy. Okay, so if I'm doing this, then I can, over C, I can restrict to just considering one Cartan subalgebra. And, well, secondly, if HC normalizes my subalgebra, so that's another way of saying that it normalizes, so the product of anything in H with anything in A lands again in A, then this AC has a root system with respect to HC. Okay, then the root system of AC with respect to HC, maybe we denote it, maybe psi of AC and HC, okay, is a subsystem of the root system of GC with respect to HC again, okay, and we denote that phi maybe, okay, so that will be a subsystem. And the algebra is, of course, completely determined by this root system because, well, when you know the roots, then it's just the root vectors, and you take the algebra generated by the root vectors, and then you're done, okay? So now we have another fact, which is that two subalgebras, A1C and A2C, are, let's say, GC, I will say what GC is a bit later, in a minute, GC conjugate, if and only if their root systems, psi of A1C HC and psi of A2C HC are W conjugate, okay, where W is the Weil group of phi, And this GC is, let's say, the adjoint group of GC, where the adjoint group is just the identity component of the automorphism group. Okay. So this gives you then an algorithm to classify. It even gives a brute force. If you didn't know this Dynkin trick with the pictures and so on, it even gives a brute force algorithm. You just take all subsets of phi, throw away those that are not root systems, and then do conjugacy by a finite group, which is a Waal group. Okay, so very nice brute force algorithm, but of course the Dynkin trick is much better. Okay, so this solves the problem for regular subalgebras over R. Very nice algorithm. Sorry, over C. Now we do it over R. And over R, there are a few things that are no longer true. There's not a unique Cartan subalgebra over up to conjugacy, but there's there are finitely many. So that's good, finitely many. Well, and of course the Waal group is not well. So how does it work over R? Here there are finitely many Cartan subalgebras. So let H be one of them. Well, up to conjugacy, right? Let H be one of them. So just pick one. Then we say that subalgebra A in G is H regular if it's normalized by H. That seems to be very, very good. But we need a second definition here, and we say it is strongly H regular if H is a maximally non-compact Cartan subalgebra, which I abbreviate as CSA, Cartan subalgebra. In different part of algebra, this is central simple algebra, but in the Lie theory, this is Cartan subalgebra. Okay, so if H is a maximally non-compact Cartan subalgebra of the normalizer, let's say the normalizer in G of A. And I will not say what maximally non-compact means in this case. The point of maximally non-compact is that, again, the maximally non-compact Cartan subalgebras are again unique up to conjugacy. And therefore you can have a theorem which is analogous to the one over there. So maybe let me write it down now. I'm going through kind of non-linear way through these blackboards, but anyway. Okay, that's actually also, let me put this back. So now we have a theorem that says that the subalgebras A1 and A2 in G are G conjugate, and I will say what G is in a minute, if and only if the psi of A1C and HC, so you complexify it and you get again a root system, no? And the psi of A2C and HC are maybe WH conjugate. Well, that's actually so strongly H regular, so that's forgotten. Strongly H regular subalgebras. Okay, so two strongly H regular subalgebras are G conjugate if and only if the root systems that you get if you complexify both are conjugate on the W of H. But W of H is not the same as W. Okay. So what is G? Here G is the adjoint group of G. So that's sort of similar, but in this case, for this adjoint group, you take the identity component of the automorphism group with respect to the Zariski topology, and here you do the same, but then with respect to the Euclidean topology. Okay? And W of H is the quotient, is defined as the Waal group, but then with this group. So that's the normalizer in G of H divided by the centralizer of G in G of H. And this group is naturally a subgroup of W. So this is a subgroup of the Waal group. And with Heiko, we have an algorithm to compute it, which in itself is a very, very long story, because 5 years ago we also had an algorithm to compute it, but then we found out that it was wasn't right. It wasn't right in a few cases. So actually it needed an extra hypothesis. It only worked correctly for, well, a subset of the things that we were interested in. Anyway, but now we have a better algorithm which we believe to be correct. Yeah. It's not actually not easy to compute this thing, but yeah. Okay. So, how do things work now? How do you find now these regular subalgebras? Well, you start with, so idea of algorithm, it's a very crude thing. Start with the complex subalgebra, which is H or C regular. You found that by Dynkin's algorithm. And then you just let the Waal group act on the root system. So then W, so the big Waal group, acting on the root system of AC and HC. This now gives all conjugate subalgebras that are HC regular. All right, because two subalgebras are conjugate if and only if the root systems are conjugate under the Waal group. So the orbit gives all possible root systems of all possible, gives all real, well, all subalgebras that are GC conjugate. So all subalgebras of GC conjugate to AC. Okay, and then you pick the one, you throw away the ones that are not defined over the reals, so we do not have a basis in your real form. And then you, with this criterion, with this theorem that I wrote down, you sort of get rid of the conjugate copies. And that way you get an algorithm that actually you press a button, and in the end you find all regular subalgebras of your real form up to conjugacy by the adjoint group. No, it's just pressing a button. No, that's very good, as we heard before. Okay. So that's a very nice. It takes a while. Okay, it takes a while because you have to do some trickery. Of course, you don't compute this orbit, at least not for E8, for example. But there's a stabilizer. We'll have a stabilizer, for example, and things like that. So you need to do some tricks, but it works even for E8. So now can say maybe 2 words or 3 or 4 or 5 or a few more on the S subalgebras. So S subalgebras, those that are not contained in a regular subalgebra, regular. Okay, and there's actually very few of them. So in the exceptional cases, Dynkin classified all of them. And he has some handy theorems about them and things like that. They're not contained in any regular subalgebra. Okay, so so how do we go about? Let's see, how are we doing time? Okay, 10 minutes. In order to sketch, I'm only able to sketch because of time. Sort of how we go about those. Here the life is much more difficult than for regular because we cannot use these root systems and while groups and things like that. Actually, we cannot do conjugacy either. We just do it auto isomorphism. Okay, and so how does this work? Well, maybe in order to formulate it, I need to say something about real form. So what is a real form? So GC, this is simple over C. Then a real form, G of GC, is the real span, is the R span of a basis of GC, and which is closed under the bracket. Okay, so it's yeah. So that's a real form, and the real form comes with the conjugation. So this gives me a map sigma from GC to GC, given by simply by sigma of x plus iy is x minus iy, where x and y lie in G. Okay, and that's a corresponding conjugation. Now, what we have next is a so-called compact form. So there exists a compact form. So U of GC with a corresponding map tau from GC to GC. Such that tau and sigma commute. Okay, such that tau sigma is equal to sigma tau. And then we set theta equal to tau sigma. This now is an isomorphism. So these are these tau and sigma, they are anti-involutions, as they're called, because they don't respect scalar multiplication. Okay, so if you do sigma of lambda v, for example, then you get lambda bar sigma v, and not lambda sigma v. But the product of two anti-involutions is a normal involution. This is an automorphism of order 2. So this means that G is equal to G1 plus G minus 1, and these are the eigenspaces of theta. And this is actually called, K, and this is called P. K for compact, and P for, I don't know. So, okay. Now, my erasers went up. Then take one which is still down. Now, what we also do in this case is we look at a slightly different setup. So we let maybe epsilon from GC to G tilde C be an embedding of complex, semisimple Lie algebras. Okay, so we start again on the complex. We know a complex, so the idea is this would be, then the image of epsilon would be a maximal S-subalgebra in this case. And then we fix a real form of G of GC. So you take a real form of this thing, and you wonder what real forms of that thing exist, such that epsilon maps the real form here and the real form there. Okay, so then the real forms G tilde of G tilde C with epsilon of the original real form is actually contained in G tilde, they sort of arise in the following way. Or they can all be constructed in the following way, maybe. One, first, well, we fix a compact form U of G. Then there is a compact form U tilde of G tilde such that epsilon of U is contained in U tilde. Okay? So you fix a compact form here, and then there is a compact form of that such that epsilon maps this compact form into that compact form. The existence of that is a consequence, for example, of the so-called Karpelevich-Mostov theorem, but I will not go into that. So we have this, and let maybe tau tilde be the corresponding conjugation. So the tau tilde is the conjugation of G tilde C with respect to U tilde. Okay, and then 2, there is an involution theta tilde of GC tilde with epsilon theta is equal to theta tilde epsilon. So this basically means that theta tilde takes the values that theta does on the image of epsilon. Okay, so this is epsilon maps this into that, so there is a little piece of G tilde C is actually isomorphic to GC, and on that the values of theta tilde are prescribed. Okay, and such that theta tilde commutes with tau tilde. Okay, and then if you have this, then we said, well, maybe I will finish this on the next blackboard. Why not? Let's have this. Then we said, not said, then our U tilde is actually U tilde 1 plus U tilde minus 1, which are eigenspaces of theta, theta tilde, sorry. All right, and we said K tilde maybe, because we use tildes everywhere, equal to U1 tilde, and P equal to I times U minus 1 tilde, and G tilde equals to K tilde plus P tilde. And that's it. Okay? This is now the real form that we constructed. And well, in order to make this work in practice, so what we have epsilon, and we can fix our compact form we have as well. But to find the compact form such that the epsilon of U is very difficult, so I don't know how to do that. So that makes it a bit difficult to execute, of course. So in practice, we replace epsilon by phi epsilon for some phi in the automorphism group of G tilde C to ensure that epsilon of U is contained in U tilde, where U tilde is a fixed compact form of G tilde C. Okay, so I don't know how to find the compact form, but I know how. Well, I actually don't know very well how to do that either. But in the cases that we did, right? So all these things up to rank 8, it was always not well. I will not go into it, but there were some tricks. So in general, I don't know how to do it, but they were sufficiently nice that we could actually find this phi. Okay. And then what we do, well, once you have this, so you have this, and now you have to find this involution theta tilde. And what you do is, what we do basically, is to translate all these things into equations. So this we can translate into linear equations on the matrix entries of theta tilde. So this will become linear equations, and here we'll get polynomial equations. And well, there's a lot of trickery you have to do because you have to split the real part and the imaginary part, because this and these things are well, anyway. But anyway, you get lots of polynomial equations, and then we do what Ellen did, compute Gertner bases, and actually then you get solutions, and you go through all the solutions, and that way you construct all the real forms. Okay, so this is much weaker than the regular subalgebra thing, because it doesn't do it up to conjugacy. It does it up to isomorphism, actually. So it just finds one copy in one real form, right? Yes. And actually, if you do it, you can do this also for other subalgebras. You can actually do it for all subalgebras. But if you do it for S-subalgebras, it is a practical observation, which I cannot prove, that the number of solutions of your polynomial equations is always finite. Actually, in practice, it's usually 2 or 3 or something like that. Okay, so and then the Gertner base is extremely easy. There's sort of equations like x1 squared is equal to 3, which of course you solve by saying x1 is equal to root 3. Yeah, so in practice it actually works quite well. But I have no idea why. Actually, for S, so if you do it for other subalgebras, which are not S subalgebras, then you can get equation systems that have an infinite number of solutions. Well, and then of course you're a bit lost, because to find all real forms you would have to go through all these infinite number of solutions. And that's but for the S subalgebras you always get a finite number of solutions. Okay, I think I will stop there. Thank you.
I mean, there are 2 questions, the second being more important than the first. One is, can you give us any indication as to how this helps us to understand black holes and string theory? And the second question, which is more important, is, does this help with graph calculus? I mean, the connection of string theory.
With Heiko we got a grant application for, well, not for this actually, but for something similar to do with, well. And we were in Australia, and we got it funded, and we wrote in it that actually it has to do with black holes. That has to do with black holes as well, actually. So, that's the more important question. The answer might be yes, but of course they didn't write it. You know, they didn't write it because of your nice applications. You get the money. They just wrote you get the money and didn't really write why. And to your first question, I don't know, because I must say, working with physicists. So Alessio Marrani is not the first physicist I work with. We've also worked with Heiko and Mario Trigiante, for example. It was another person into black holes. At first I thought, now I'm going to understand some physics, and I asked him exactly the same question. But then there comes along, explains, very eloquently, but after the 2 or 3 words, I'm already lost, okay? So I'm always very jealous of physicists if I work with them, because they can more or less understand what I do, but I have no possibility at all to understand what they do.
Yes, I think that's true for all of us, yes.
Linear algebra? Yes. So these linear equations, yes. Yes. But the linear algebra in itself is not really the problem. It's more setting up the equation. So the main bottleneck in time-wise is, for some reason, is actually setting up the polynomial, not solving them, because once you have the polynomial equations, the Gertner basis goes, and you get your finite, very small number of solutions. But setting up these equations is a rather dirty job, right? But somebody has to do it. Yes. And that takes a lot of that takes the bulk of the time. Not the linear equation. The linear equation also takes some time. So maybe what you mentioned to me maybe would help there, but it's not the main part of the problem.